Okay, 732, right? An ideal buck converter. V in is 15 volts, V out is 5, switching is 100 kilohertz, maximum output power is 100 watts. Okay, okay, see this, the circuit is designed to operate CCM down to 10%. So that's boundary conduction mode method. And percent peak-to-peak output voltage ripple of 2%. Assume all components are ideal and the L value selected critical inductance value. That's the critical inductance value. All right, let's do this problem. So what we have is we have a buck converter, right? Fifteen and 5. Okay, 15 volts and 5-volt output. Okay, and then 100 kilohertz switching frequency, and then what else? 100 watts. So that's the maximum, 100 watts. Okay. Peak-to-peak output voltage ripple of 2%. So plus minus 2% V out peak-to-peak. Okay. All right, the critical inductance and its peak current rating. Yeah, so that's based on this one, is given as 10% load.
Yeah.
So critical inductance is at 10% load. 10%, okay. So what's 10% load? So that's 10% of 100 watts, which is equal to 10 watts, right? And this translates into I out min average, right? The average of the output current at minimum wattage at 10 watts is equal to 10 watts divided by 5 volts. That's 2 amps. Yes? So now I know that the critical inductance is found at 2 amps, meaning the boundary conduction mode occurs at 10% load. So if I were to draw the inductor current, it will look something like this at 10%. Okay, so at the 10% load, the average of the inductor current, this is at 10%. It's 2 amps from here, right? So therefore, if the average is 2 amps, I would know delta IL. Delta IL would be twice that much. It's going to be 4 amps. Is that good?
I see.
Yes?
Yeah.
Okay.
So
now,
when you have I out max and I out min, you can't subtract those and say that it's delta IL.
yes, delta IL is always IL max minus IL min. It's always the same.
But not the
Equation is
average
always
of those.
the average. The average.
Like
The
if
average.
I said like I out max is 100 watts divided by 5 volts, that's 20 amps. And then I said I out min is 2 amps. I can't say 20 minus 2 is 18. And that's delta IL.
20 minus 8. Say it again. So if let's say it again.
If I found I out max, which was 100 watts divided by 5 volts, that's 20 amps. And then I took 10%. I took 10% of that.
Yeah.
Which is 2 amps.
Yeah.
I can't say 20 minus 2 equals 18 amps, and that's delta IL.
No, this is average value. Both of them are average value. So
Okay.
you have average value at maximum load and average value at minimum load. So uh,
Okay.
what happens is that the 20 amps, that's happening at 100 watts. So imagine at 100 watts, this triangle is going to be going up here somewhere,
Mm-hmm.
right there. That's at 100% load. And the average of this, that's the 20 amps,
Okay.
right? Now, yeah, if you try to find delta IL from 20 amps, you cannot because, this is nothing special about CCM here because, we don't know what IL max is. We don't know what IL min is, right? So it's hard.
Mm-hmm.
The only one you know is 20 amps. But VCM is special, right? VCM is special because IL min is zero.
Yes.
So see, go ahead and put IL min there. So delta IL at VCM is equal to IL min minus IL max, but IL min at VCM is equal to zero. See that? So
Yes.
therefore, delta IL is equal to IL max, which is the case right here. See this?
Yeah.
Delta IL is equal to IL max. That's why finding critical inductance can be achieved by using boundary conduction mode, because that's when IL min is equal to 0 amps.
Okay.
Yeah. Okay.
That makes a lot more sense now.
Yeah. So now from here I can find LC, right? Critical inductance. I out IL min is equal to I out min average minus delta IL over 2, right? And from here, I know IL min is equal to 0 at boundary conduction mode. And then I out min is 2 amps. And then delta IL is, well, actually, I know delta IL already. I don't need to apply this equation anymore to find L.
Yeah.
I know that VL is equal to L delta IL delta T, right? So
Mm-hmm.
there's the L I'm looking for. So L, which is equal to LC now, is equal to VL times delta T over delta IL, right?
Mm-hmm.
And I can use voltage when it's on. What is the voltage again when it's on? I forgot.
V
V in,
in
right?
minus V out.
Oh, when it's on, it's V in minus V out. Yes. So that's 15 minus 5. So that's 20. And
Mm.
then delta T is just dt.
Isn't it 10?
Wait, is it 10? Yes, it is 10. My algebra is wrong. It's 15 minus 5. You're right. Something wrong with my mouse. 15 minus 5, yes. It's 10. And then dt, right? That's duty cycle. You know the duty cycle, don't you? This is
You
for,
find it. It's 1/3.
yeah. So duty cycle, that's dt, isn't it? That's dt. So that's 10 over 4 times the switching frequency. What was switching frequency?
100 kilohertz.
100K. And then the duty cycle is 5 out of 15 for buck. That's it, right? That's the answer for L.
Yeah.
And then for the next one is capacitors, capacitors value and its voltage. Oh, actually, no. Peak current rating of the inductor. So what is that equal to? That will be found on which condition? 100% or 10%?
100%.
100%, yes. So now you need to know that value right here, peak value. What's that peak value?
22.
ILMX, 22, yes. 4, from peak to peak is 4. So therefore halfway is 2 amps. So therefore that peak value is 20 plus 2, that's 22. You're correct. Okay. And then capacitor's value and its voltage rating. Uh, Yeah, for this one, I would just use the equation that I have. I don't want to derive it here. Um, so we have the equation for voltage, right? For capacitor, right? For C out, for a buck converter.
I actually have a question.
Uh-huh.
Most of the time you only give us percent peak to peak voltage ripple,
Mm-hmm.
and that's the same as delta V out over V out average. So we don't
That
have
is
to do
correct.
anything there,
That's
except
correct.
when you give us the percent, but the only thing we need in the equation is delta V out. We should multiply the percent by V out to get that delta.
You could do that, but I thought the equation can also use delta V out over V out, which is already in percent. Is this right here? See this?
I think it's input capacitance that usually does that.
No, right here. Is this buck or what is this for?
Oh,
I
well.
believe this is buck, right? No, this is not buck. Let's go to buck converter. Output capacitor. That's buck boost. That's boost. So for a buck, hopefully this is buck. It is buck. For the output capacitor, yeah, right here. There's delta V out over V out. That's already in percent.
Mm-hmm.
Yeah, so I can use that equation. So C out is equal to D over, let me write it down. Oh, where's my, C out is equal to, I already forget. The D over, okay. D over delta V out over V out times the frequency. Yeah, frequency and R out min. Okay. Frequency and R out min. So make sure you have this equation ready, otherwise you're gonna have to derive this. Okay, so duty cycle we already know, right? Duty cycle is 5 over 15. So let's just use this. So this is equal to duty cycle, which is 5 over 15. Delta V out over V out, that's 2%, isn't it already?
Mm-hmm.
That's given in the problem statement. And then F is 100K. Then R out min is equal to V out over I out max. Be careful because that's R out min, right? You want to get the worst case scenario for capacitance, so that occurs um, at larger current, right? So that's going to be 1/3 right here, 0.02 right there, 100K right there, and then V out is 5, I believe, right? And then divided by I out max, which was 20, wasn't it? 20
Mm-hmm.
amps. So right there is the C out. Does that answer your question?
Yes.
Okay. And then the second part of the problem is asking for voltage rating. Now this one, um, voltage rating of VC out, uh, I could accept two answers. The first one is just V out, right? Average, which is equal to 5 volts. Or if you want to include the ripple, that's fine too. I'll accept either one. It's fine with me. Like this. Um, was it 5%, right?
It's 2%.
Oh, 2%, sorry, 2%. So yeah, either way is fine. Actually, this 2% is peak to peak. So divided by 2, I almost forget. Right, so you have, if I were to draw the output voltage is going to be 5 volts average, and then around it is peak-to-peak ripple like this, right? So that peak-to-peak ripple is 2% of 5 volt. So therefore, peak, if you want to include the ripple, that peak right there should be 5 volt plus 2% times V out over 2. Do you agree with that?
Yeah.
All right. And then the next one is, let's see if there's more people joining us.
Wait, also, when you're
Go
done
ahead.
with that, could you go back to what you just had on the screen for a
Yeah,
second?
sure. Now I'm checking to see if there's somebody in the waiting room. Looks like there's nobody. Okay. All right. Which one?
The one we were just doing, finding the voltage rating for the capacitor.
Yeah, this one.
Yeah, on the left there, right above where your cursor is, why do you, how is that different from, like, why is that different from what's on the right?
Well, this one is just the average value, 5 volts. This one you add the peak, half of the peak-to-peak ripple.
But why did you write that the peak for the capacitor is equal to the average value?
Like this one, I said
Yeah.
I accept either answer.
Oh,
So
okay.
yeah, if you answer this way, I'll accept it. If you answer this way, I'll accept it as well.
Just because it's so small.
Yeah, exactly. Because
Okay.
2% of 5 is what?
Yeah,
Uh,
okay.
it's like 0.01, right? And then you divide it by 2.
Okay.
So yeah, I'm not gonna make a big deal out of very tiny voltage out of 5. So either way is fine with me.
Okay, thanks.
Yeah. And then voltage and current ratings of the switch. Uh, voltage and current rating of the switch. What is the voltage rating of the switch here?
VN.
VN, yes. For a buck converter, is equal to VN, which is equal to 15 volts, right? And then I switch average, that's the current rating of the switch, that's equal to what? DI out, right? Sorry, DIL,
Yes.
right? But this has to be done at maximum load. And for a buck converter, right, for a buck converter, this is equal to D times I out. You agree?
Mm-hmm.
So I have to find it at the max load condition, which is the 100 watts, right? Which gives this happens at 100 watts, which give us what was the current? 20 amps, wasn't it?
Yes.
So therefore, I switch average is equal to duty cycle, which is 5 over 15 times I out max, which is 20 amps. Any question on that?
So you called this a rating. So again, isn't the rating, wouldn't that be like, or or if you wanted to do like the peak current, when would you find like IL max? Because that's technically like the highest current that it sees.
No. So uh, for voltage rating of a device, what we need to find is the absolute value, which is the max value or the peak value for a device, such as switch, diode. But for current rating, we don't look for absolute value. For current rating, we look for average value.
Okay.
That's the difference between the two, right? If you look at way before, like early in chapter 3, perhaps chapter 3, we talk about devices, right? Switching semiconductor devices. And I mentioned there that for voltage rating, you need to find peak value. But for current rating, you need to find average value.
Yeah. I
So this is
remember.
not peak. Yeah, so you're right, this is not equal to peak value. Definitely not. But for rating, we don't need to find peak. For current rating, We don't need to find peak value. We need to find average value.
Okay.
Why is it that the average, that we can use average for that instead of peak? Like, why doesn't the max matter as much for current?
Yeah, this has to do with 411, but I can tell you right now, current rating of a device is related to temperature, right? The ability of a device to handle temperature.
I see.
And temperature of a device is going to be a function function of the average value of the current, right? So um, if you use peak, it won't make sense because let's say I have a switch right here, right? And current through the switch is this right here. Let's just say, okay? And then I have another current flowing through the same switch, and that same current gives me this current right here. There. Which one do you think is going to heat up more? First current or second current?
The second one,
Exactly. Why?
because it's has a higher average, it's longer.
Exactly. Because the device is experiencing more current here, even though the peak is less than the first peak. See that?
Mhm.
That's why we don't use peak value for current rating of device. Because as you can see from this example, a current can have a very high, very tall peak, but that doesn't make a good it's not going to give the device what do you call it the increased temperature or the it doesn't give the device anywhere close to the temperature rating of the device if the duty cycle is very tiny, right?
Okay,
So having a big duty cycle with lower peak, that would actually increase the temperature of the device closer to the limit. So
okay.
hopefully that answers.
Yeah, thank you.
Okay. Um, voltage and current ratings, voltage current ratings of the diode. So that would be the other way around, right? So diode is going to be 1 minus D times I out max, right? So that's going to be 1 minus 5 over 15 times I out max, which is 20 amps. How about voltage? That would be peak value. What is voltage across the diode, rating wise?
Isn't it also 15?
Yeah, so when the diode is open, that means the switch is closed, right? Right here. When the diode is open. So here's my V in. So therefore, voltage across the diode is also V in. Yeah, so it is V in. All right. That's one last one, right? Total RMS value of current through the capacitor. Okay, what is that equal to? For a buck, this is referring to the output capacitance, right? For a buck converter, the current through the inductor is a triangular waveform, and so therefore current through the capacitor will also shape the same way. It's going to be a triangular waveform like that. Yeah, that. Let's see, like this, something like that. All right. So that's 0 amps, and what is this right here from here to here? What is delta IL? Found it earlier.
Isn't it 4?
That's correct. Yeah, delta IL was found to be 4 amps earlier. So therefore, from here to here is 2 amps, right? And so the RMS for output capacitance of a buck, that's easy, right? That's just a triangular waveform. So I C out RMS is equal to delta IL over 2 over root 3 for triangular waveform, right? That's going to be 2 amps over square root of 3. Okay. Any question on this? Okay. If not, any more questions from you, Jordan?
I do have questions, but
Okay.
I don't know who was here before me.
What is the what?
I don't know who was here before me, but I do have questions.
Go ahead.
Okay, my question is for chapter 8, a problem 42.
42.
I was trying to solve it yesterday, but I got confused on some concepts. I mean, if we can go over, that would be great, but like there are some concepts that I think I'm missing.
Yeah, we can go over this.
Yeah.
All right. So this one is push-pull. Figure 810 shows the input current waveform of an ideal push-pull converter right here.
Mhm.
Yeah, I'm actually planning to go over this problem anyway, so this is great. So let's see. Input current of an ideal push-pull converter operating a steady-state CCM. The transformer used in the converter has turns ratio. If the input voltage is 12 volts, then calculate the average current to each switch. All right. Okay. So we have, oh yeah, sorry. What happened here? Here. So we have the current waveform at the input of a push-pull. Right. So that's the I in of push-pull. Right. So let's draw a push-pull. Happen here. There you go. So push-pull. There. All right. That's diodes here, diodes here. Yeah, tell me what we know again from the problem. We know the current waveform here, right? That looks like this. Yes. And what is the value here?
6 and 8.
I'll just take a look.
It's 6 and 8.
6 and 8. Okay. 6 and 8. And then 4, 10, 20. Right? Something like that. That's microseconds. What else do I know? I know
The MP and N2.
NP, NPNS13. Okay.
Yeah.
1, 2, 3. Okay, what else do I know? I know the input is 12 volts. Okay, anything else I know? Is that it?
Well, I don't know if this is, I mean, this is already implied, but I put it, since it's push pull, that the max duty cycle is going to be 50%.
Oh, yeah. Yeah. Yeah, that's good. Okay. But
And it's
these are the,
also in steady state.
yeah. Great. Okay. So what's the first problem asking? First problem is asking average current to each switch. So, uh, so what we are given is the input current waveform, right? Here's the input source, the source right here, and the current supplied by the source, this current right there. And as you can see, this current splits into two, up and down that way. Yes. So now I know that by KCL, this current right here is actually I switch 1 plus I switch 2, right? Because they split. So if I want to draw I switch 1 and I switch 2 from this current, then I could, right? It's going to be like halfway. So it's going to be switch 1 is going to be the first set right here. And then after 20 microseconds, it repeats again. It repeats the switch. And then here's the 10, half of the period. And here's the 30 right there. So if I were to draw IS1, IS2, that's what I'm getting. Is that okay so far?
Yes.
Okay. So notice that if I add IS1 and IS2, I get this current, right? So then the question is asking for average current through each switch. So that means what is the average value of this current right here or this current right here, which is the same, right? Same average. So it's going to be half of these, right? Or you can just find the area of the trapezoid, right? What's the area of the trapezoid here? Well, I know the points right there, 6, 8, 0, and 4, right? So area of trapezoid is equal to the summation of the height. So that's 6 plus 8 times the base, that's 4 microsecond, right? That's the area divided by 2, right? Okay, and then the whole thing, if you want to find the average, so the average would be A1 divided by the entire period. The period is not 10, right? The period is 20, right? The period of the current through the switch is not 10 anymore, but it's 20. Does that make sense? Yes. So that's the answer for this. We got 14 divided by 2, 6 plus 8, that's 14, right? Divided by 2, that's 7. 7 times 4 is 28 microseconds, right? And then divided, no, is that right?
Let me
And then
calculate it real quick.
microseconds amps, I believe. So that's amperage, right? And then 28 microseconds amp divided by 20 microseconds. That's equal to, what is that? 1.4?
Mm-hmm.
Is that the answer?
Yeah. So this makes sense. But when I was looking at the solution, which also makes sense, but on the solution, it was saying that okay, the average the average current was going to be equal to the average of the inductor current times the dirty cycle, which makes sense, and I get the same answer. But my question is the current through the inductor the same? Like it stays the same? Because I try to like put what I got for the current on the second part, which is like the current through each dial, and I was not able to get the same answer as the solution.
Wait,
So the solution the solution for this, the one that you provided to us, shows that we found the average current through the inductor and multiplied it by the dirty cycle, and with that we were able to find the average current of the switch.
are you sure? That's okay.
So yeah, so, and then I was like, well, if I get the same concept and this is derived from a buck converter, then I'm just going for the like current through the dial, I'm just going to do like time off times the average of the inductor, but it didn't work like that. Maybe I'm just like
Uh,
getting confused, but yeah.
let me look at the solution. That doesn't
Professor,
make that doesn't make sense to me.
isn't it also that the average of each switch is half of the input current? So if we get 1.4 for the input current, we should be getting 0.7 for the inductor current, or for the switch current, sorry.
The average of the switch current is half of the average of the input current, yes.
Mhm. I can show you what I did, Professor, if that's okay with you.
Oh, hang on, hang on.
Yeah.
Let's solve it one at a time. Otherwise, I
Mhm.
get confused.
Yeah,
Okay,
yeah, for sure.
let's go through the solution that I gave you. That's
Mhm.
what is it again? 742?
842.
842, sorry, 842. Because what you said doesn't make sense to me. 842. So I'm using inductor current to solve IN.
Mhm.
No, I did not. I used actually no. I did exactly what I just did here. I'm looking at the solution.
Okay,
All right,
you
so
look at
let me share the screen. You see this, right? Is
Yes,
that
I
what you
see it.
see?
Yeah,
Yeah.
yeah.
So I use ILP min, ILP max, and that's what it is, right? It's the primary side of the inductor current. So if you look at this trapezoid right here, right? Um, the peak right there is the same as IL peak, right? The peak of this current, the inductor current. But you reflect it to the primary side, right? So that's called ILP max. And this one is ILP min, which means this is the same as the peak current of the inductor, but reflected to the primary side. So if I were to draw the current here through the inductor, it will look like this, right? Agree? Yes?
Mhm.
And
Okay.
yeah, and this peak right here is called IL max, and this min is IL min, right?
Okay. Yes,
But then it,
but
but then that's on the secondary side. If you move it to the primary side, it becomes ILP max, ILP min. So it's just a name I gave for 6 and 8, which they are. 6 amps is ILP min, and 8 amp is ILP max. So that's exactly the same as what I did here, right?
it is exactly the same. Yeah.
Yeah,
Okay,
yeah,
but
exactly the same.
okay, so but this is just like as the area instead of the average of the inductor, which is the same. Yes, it is the same, but when I use it to solve part B, it doesn't work like that. So
No,
my question is,
first of all, this is area. I'm finding area right here.
you're
Okay.
coming area. So this is not the average of the, okay, so that's I misunderstood that because IL average is also IN min plus IN max over 2. And then if I do dirty cycle is also T on over TSW, which is the same thing, and I get the same
Yeah.
answer, but my concepts were different, which is why I wanted to talk to you about it.
Yeah, for the solution, I just named those values to be ILP min and ILP max, right? Whereas over here, the way I solve it, I just put the numbers. It's the same way. It's the same thing. This is just naming them, finding the solution by naming them first. So it should be the same.
Yeah,
Yeah.
it's just a misunderstood because I was like, okay, so if I take the current through the inductor, which is what we found, I assumed that it was the current through the inductor, the average current through the inductor, then I could apply it to this to part B. But no, I cannot do that. So
Right,
that's why
right,
I wanted to talk to you.
right. Yeah, yeah. So yeah, again, as I said, I'm just naming those points. ILP min, ILP max. Yeah, and then find the average value that way, which is exactly the same as what I'm doing here.
Okay.
Okay.
Mhm.
So that's part A, and then what Jordan said earlier is that it's true that I in should be twice of the I switch average, or in other words, I switch average should be half of the I in, right? That is true. So I in average should be twice I switch average, right? And that should be apparent from this picture that the entire input current has 2 pulses per 1 period, whereas the switch only has 1 pulse per period, right? Okay. Any more question on part A?
So what will be the final answer? 1.4?
Say it again.
What will be the final answer for that one?
The 1.4 amps, isn't it?
It
Right?
is.
Yes.
Okay.
If you look at the solution, it is 1.4 amps as well. Yeah. So that agrees with my solution. Yes. All right.
Mhm.
Part B, average current through each diode. So this one is on the output side. That's on the secondary side. So that's the thing about isolated converter. You have to really make sure you know whether or not you're working on the primary side or on the secondary side, right? So I diode is on the secondary side. And what is it asking again? Man, average current through each diode. So if you look at the topology right here, right? Here's IL right there, and here's I diode 1 and I diode 2 right here, right? Again, by KCL, I know that IL must be equal to I diode 1 plus I diode 2 by KCL, right? So therefore, IL average should also be I diode 1 average plus I diode 2 average, right? And since diodes are equal, so therefore, IL average, I should probably put it right here. IL average is equal to I diode 1 average plus I diode 2 average, right? But I diode 1 is equal to I diode 2, so therefore it's going to be equal to I diode average right here. Since I diode 1 is equal to I diode 2 average. Okay? Or in other words, I diode average is equal to IL average divided by 2. And for a push-pull converter, since it is derived from a buck converter, you can see that IL average is the same as I out average right there, right? So IL average is equal to I out average. Any question on this? Let's see if we can.
How can we use that one instead of using our like duty cycle equations? So it's like I diode is equal to I inductor times 1 minus duty cycle.
Oh, not anymore. Not on push-pull. Because we are in push-pull, we have 2 switches, and when the switches are off, diodes are still conducting. Remember when the switches are off, diodes are still conducting. It's not off. They're not off.
Yeah.
That's why you cannot use 1 minus D anymore.
Okay.
Yeah.
Oh, okay. That was my mistake. I tried to solve it like that. Okay.
Okay. Yes.
Okay.
Yeah.
Learn by doing. Learn by doing.
Okay. So then, do we know I out average?
Yes.
Well, I know what the in is, right? Since this is ideal, therefore P in is equal to P out, right? Do we know P in?
Mhm.
Yes, right? P in is equal to V in times I in average. P in, oh, V in is, oh, was it 12? I don't remember exactly.
It's
Yeah, it's
12.
12. So V in is 12. I in is twice of I switch average. So that's 12 times 2.8, right? 1.4 right there times 2 That's 2.4 amps. Okay.
2.8.
What is that equal to?
It should be 12 times 2.8. Not 12 times 2.8.
2.8. Gosh, yes, 2.8. And my algebra is messed up. What is this equal to? Whatever it is, right? 12 times 2.8. So that's equal to P out. So therefore, P out is also equal to 12 times 2.8. There you go. And so from there, I know I out average. I out average is equal to, what do we know? V out average?
No, we don't know the
Oh,
out.
well, but we will.
We
Because I
will.
know
Mhm.
I know what the turns ratio is, I know what V in is, and I know what
Yeah.
duty cycle is.
Yeah, yeah,
Right.
yeah, for sure.
Yeah, V in is equal to 12. Turns ratio was 1 to 3, I believe, right?
Yeah, 1, 2, 3.
And then what is duty cycle equal to?
The recycle is equal to 0.2.
0.2. So duty cycle is equal to 4 microseconds out of
Over
20.
20.
So duty
0
cycle is equal to 4 microseconds out of 20 microseconds. Yeah. That's 1/5. 1/5, sorry.
Mhm.
So that's 20%.
Mhm.
All right. So therefore, V out is equal to V in, right? V in times duty cycle times 2. Almost forgot the 2 because that's push-pull, right? 2 times V in times duty cycle times, oh, what was it? N3 over N1? N2 over N1, I believe, right? So that's going to be, am I right? The equation from the book,
That's right.
right? Okay.
That's-
So what is that? What is that equal to? And somebody, 24 times 3, 79. What is that? What is the whole thing equal to? Anybody?
I got 14.4. Oh, I probably made a mistake.
Well, let's look at the solution. Solution should be,
It says 14.4.
Oh,
yeah,
I
right
got
there.
it right.
Yeah, right there.
Okay, it's
14 point.
right.
Okay.
14.4.
Okay. So 14.4. Now we have the output voltage. We have the output power. What is output power? P out is equal to 12 times 2.8.
It's 33.6 P out.
32.6 right there, yes. 33.6. All right. So now I know I out average, right? Which is P out over V out. That's going to be 33.6 divided by 14.4. Whatever that is.
It's 2.3.
Right there, yeah, 2.3. All right. So therefore, I diode average must be half of that, right?
Mhm.
1/6.
1.1.
Yeah, 1/6. Yeah.
1.16. Yes.
Okay. All right. Is that good?
Yeah, that's perfect.
All right. What else do I have here? RMS current to the output capacitor. RMS current to the output capacitor. Ooh. Okay. I of C out, right? RMS. So we know that for a push-pull is derived from a buck converter, right? So we have the same output stage like this. And Therefore, the shape of the current through the capacitor is going to be triangular waveform. Right, it's going to be like this. Right, we just need to find peak-to-peak ripple on this one. Right. So what is IL max? Well, what is IL min? Right. Do we know this? We should, right? Because we know the reflected value on the primary side is 6 and 8, I believe. See this? 6 and 8. So I know that IL P min is 6 amps. IL P max is 8 amps. So this is on the primary side, right? Reflected on the primary side. From here, from IL max. So can we get it back to the secondary side? Yes or no?
Yes, you use the trains ratio.
That's correct. So it's going to be 6 times, okay, it's stepped up, so to be less, right? This will be stepped down because the turns ratio for the voltage is stepping up, 1 to 3. So therefore, for the currents to be stepping down, so it should be divided by 3. So now I have the peak-to-peak ripple. What is 8 divided by 3? 2 point some. No, it's not even 2 point. It's no, it is 2 point. 2 point, what is it? 2 over 3. Yeah, 2.67. So therefore, delta IL, so that's here, right? This is going to be, over here is going to be 2.67. Sorry, not this one, sorry. Over here on the inductor. The peak right here is 2.67. The low right here is 2 amps. So therefore, peak to peak here is going to be 0.67. Is that what I have on the solution as well? Peak to peak is the
Yes.
same?
Yeah.
Oh, okay, good. Great. Okay. So now, now that I have the inductor current with the peak to peak values of 0.67 amps, now I can translate those into capacitor current, right? So that's going to be the whole thing right here is 0.67. So therefore, RMS would be IC out RMS should be delta IL divided by 2 over root 3, right? So that's going to be 0.67 over 2 divided by root 3. So that's going to be the RMS of current through the output capacitor. Okay. Any question on that one? The average voltage across the inductor. This one is easy, right?
0.
0, yes. Okay. Any more
Professor, make
question
sure
on?
you put it on the beginning or something like that, so I don't miss it again.
I might put it in the middle. All right. Any question on this? If not, let's do. Oh, do you have any more questions?
Yeah, I just have a question about there's a few problems that have you calculating like max currents either through an inductor or a switch. Is that or yeah,
Yes.
if you wanted to, because like at least for the buck boost on 7.22, you ask it through the switch. Would it be the same if you asked it through the diode, I guess? Or
Yeah.
is that not going to be the same?
Well, if it's a non-isolated, such as buck boost and buck boost, keep in mind that diode current and switch current are being derived from inductor current, right? So therefore, the peak current on diode and switch must be the same as the peak current of the inductor, right? Same thing with the
Yeah.
minimum value. Yeah.
Yeah, I just wanted to make sure that I was that was correct before I actually used that. Thank you.
Yeah. Let me show you that picture so you remember. I have a picture that shows you the answer to your question. If I can find it. In a buck converter. Come on, where is it? Go right here. Yeah, I'm going to show you. See this? This is from the buck converter section. You can see by KCL, I switch plus I diode is equal to I inductor, right? So
Yeah, I get it now. Seeing this,
yeah,
the switch part is charging it, and the diode part is like discharging it, right? So
right.
they would have to meet in the middle at peak.
Mm-hmm.
Awesome. Thank you.
Yeah. So yeah, no, it's all right. So if this is X and Y, then this is going to be Y, X, and the same thing here, Y, and X, right? They're the same. Yes.
Thank you.
Mm-hmm. All right. Any other questions? If not, I was going to do the example on forward converter. Let's look at the forward converter. We did push-pull. Just right before it, 841, I believe. Yeah, right here. An ideal forward converter operating in CCM has input voltage 12 volts, output voltage 24, maximum output power of 120 watts, and then we have distance ratio, switching frequency. It's the same thing as before. Uh, Earlier in the office hours, we also have these cases. This case where the magnetizing inductance is very large, such that ILM is equal to 0. All right, so the question for part A is average current through the reset winding. Anybody knows what the answer is? Let me
So
go
through the
ahead.
winding, you said the
Mm-hmm.
current through it.
Yeah.
Wouldn't that be 0, or is that not right? Because isn't the current traveling through the magnetizing inductor, or is that not the way this one works?
No, you're correct. It is 0. It is 0. Yes. So I'm going to draw forward converter right here, right there, right there. Yeah. So if when the switch turns on, right, when the switch turns on and diode turns off, then the magnetizing inductance being charged, right? But the uh, problem states that Lm is large. So this inductance is very large in such a way that ILM here is equal to 0 amps. Okay. So when ILM is equal to 0 amps, then how much energy is being stored in LM? Any energy being stored in LM? If ILM is equal to 0, how much energy is being stored by LM in joules? How much? What is the equation for energy of inductor? What is it? From physics? 1/2 Lm I Lm peak squared, right? 1/2 Li squared. You remember this equation? Yes. So if ILM is 0, if this is 0, that means energy in the stored in the inductor LM is 0 as well, 0 joules. If that is the case, then if there's no energy being stored in LM when the switch is on, now if I turn off the switch, right, it will force the diode to turn on. But then LM is trying to discharge this way, but there's no current, right? So therefore, if there's no current, here's 0 amps, oops, here's 0 amps, then there should not be any current flowing to the reset winding here. Why not? Well, because when the switch is off, not only that LM doesn't have any current, but also diode here is off, right? The diode is off. So when the diode is off, yes?
Okay, so when the diode, I'm sorry, when the switch is on, it's when we have energy to be 0. Oh, wait. When the switch is off. Okay, sorry. I was
This
just
is
getting confused.
just to clarify something. This is only for this case because the I guess inductor is so large that there's no current through it.
Yeah,
That's what you're trying to do with this problem, right? Under normal
right.
circumstances, there should be a current going through there.
This is actually a tricky problem too at the same time, right? But I want you to go through the conceptual process first, right? That since ILM is big, sorry, since LM is big, therefore there's no current. If there's no current, then there's no energy. If there's no energy, then when we are discharging it, there's going to be 0 amps, right? And at the same time, when the switch is off, this diode is off, right? When the diode is off, guess what? This is 0 amps. So therefore, it's also 0 amps here, right? So therefore, if you are looking at this branch right here, for this condition, it's going to be 0 amps. Agree?
That's when the diode is off.
That's when the switch is off.
When the switch is off. But when the switch is off, there is also no current going to the magnetization winding. I don't know how to say that.
Yeah, that's because LM is big, because LM is assumed to be very big.
Okay, so this is when, but so when the switch is, okay, so when the switch is on, when the switch is off, the current, when the switch is off, the LM goes to the top, right?
Right.
Okay,
Yeah.
okay.
But it
And
doesn't have
then-
any energy, right? It doesn't have any energy stored, so therefore there's no current through LM here.
And the first case that we did, when the LM was super big, is when the switch was still on, right? But LM, okay, I think I get it.
Yeah, so when that doesn't matter if it's big or small, right? When the switch is on, right here, we are charging LM. But right now, LM is huge. So therefore, if LM is huge, there is no current here,
Okay.
right? But there is current here on this winding right here. There is current, but not on LM. Here's LM right there because LM is big. So
Okay.
no current through LM means no energy, right? So when the switch is off, right here, when the switch is off, then LM try to discharge through the top winding, but there is no current, so therefore there's nothing to discharge. Therefore, there's going to be 0 amps right here. At the same time, when the switch is off, this diode is off, which means the secondary winding here is 0 amps as well, which means the reset winding here is 0 amps as well by reflected current, right? So 0 amps, 0 amps, 0 amps. All of the windings is going to be 0 amps. This winding is 0 amps. That means this winding is going to be 0 amps. That winding is also 0 amps. Yes. So for this condition, when Lm is large, when the switch is off, if you look at the source current is going to be 0 amps as well. There's nothing going back to the source, to the source right there. Right? Does that make sense first? Now, I said it's tricky because the question is asking for reset winding, isn't it? If I'm not mistaken, let me go back. Average current through the reset winding and reset n equals to 3, right? So N3. So the average current through the reset winding, here's the reset winding, right? And the tricky part is that it actually doesn't matter if Lm is big or large, is big or small, right? You can see that and reset here when the switch is on. Let's see, when the switch is on, there is no current through and reset, right? And then when the switch is off, there is also no current through and reset. So it doesn't matter what Lm value is, and reset, theoretically speaking, is always 0 amps average value.
And this is only because LM is big, right?
No,
Because
no,
if
no, no,
it-
no, no,
Oh,
no.
sorry.
Could I so in class you talked about that this circuit is one of the reasons how we know LM exists, right?
Exactly.
Because otherwise there shouldn't be current flowing through that winding. The
That's
only
right.
reason why there's current present in the circuit has to do with the magnetizing inductance.
That's correct. So let me change this, okay? This has nothing to do with this problem. Let's assume Lm is not big. Lm is going to be some value, okay? So I'm going to erase this. And you'll see that this winding is always 0 amps. Okay. So let's start with, so Lm now is small, meaning there's current, right? So turn on the switch. If you turn on the switch, what happens? You have current, let me use red. You have current flowing through Lm, right? Non-zero. You have current flowing through this winding. Why? Because in this case, the top diode is on, the middle diode is off, right? So there's going to be current through this winding, right? There's going to be current through this winding. And what about this winding? Is there any current through this winding?
Which one? Can you please say it again?
This winding. This winding.
Oh, but what is the dial? Is the first dial going to be off, right?
Exactly.
So
So this
0.
diode is going to be off. So therefore, there's no current, right? Right there. There's no current through this diode. Sorry, this winding. So the reset winding at this point is 0 amps as well, right? So that's when the switch is on, right? Even with Lm small, right? When the switch is on, there is 0 amps on the reset winding. What about if I turn off the switch? When I turn off the switch, then Lm is going to discharge, right? Lm is going to move to the top winding right here, right? And it's going to discharge this current this way, right? At the same time, this diode is off, right? And this diode is on. So no current here, 0 amps, right? That means how much current through this winding right here on the bottom side? 0 amps as well. What
0
about this
amp,
winding
okay.
right here, right? 0 amps as well.
Yeah, okay.
But do we have current for the source? Yes.
Yeah.
The source now is getting current from Lm because Lm is no 0 anymore, right? So there's going to be ILM right here, which is not 0, and it's flowing this way, that way, back to the source, right? This is on right now, sorry. Back to the source, right there. Right. So you can see that it doesn't matter what LM is, reset winding, theoretically speaking, has no current, 0 amps. Doesn't matter if LM is small or big, doesn't matter. Does that answer your question? Or is there any question on this? Okay.
No, it makes sense. It makes sense. I was just a little confused. It was too much in one picture, but now like it makes sense. It doesn't matter if it is on or off. The behavior can be the same because of the L.
Yeah, the inductance, yes. Okay. All right, so that's part A. Part B, output inductance Lx in microhenries to maintain CCM down to 30% of full load. Okay. How many percent again? 30% of full load. So 30% of full load. So that's BCM method, right? It's asking for LC when at BCM, which is at 30% of full load. All right. Do we have the full load information or no? Let's see. What do we know from here? Let me go back. What do we know? We know input voltage. We know output voltage, which is good. Oh, we have output power right there, 120 watts. So that should be relatively easy. So now we have 30% of 120 watts, right? That's what is that? 36 watts, right? So 36 watts. And then we have the output voltage, which is 24 volts. Okay. 24 volts. So 30% of 120 watts, that's 36 watts. That's at VCM. And then 24 volts, right? V out is 24 volts. So from here, I can get I out. I out is equal to P out over V out. And that's 36 watts over 24 volts, right? So that's our current right there. Can you tell me what this is? That's 3 over 2. That's 1.5. Am I right? Divided by 12 is 3, divided by 12 is 2, right? 1.5 amps. And so what is LC? So right now we know that at boundary conduction mode, the inductor current looks like this. Right? It's touching 0 amps, right? And the peak value and the average value we should know. We know the average value is 1.5 amps. So therefore, the peak value is how much?
3.
3 amps, yes. Right there. So now I know delta IL. What is delta IL equal to? From here to here. That's 3 amps, isn't it? So 3 amps. And I know that delta IL, VL is equal to L delta IL delta T, right? So therefore, I'm looking for L, which is equal to LC in this case. So VL times delta T over delta IL, right? So what is VL equal to? Well, I'm going to use the T off because when the switch is off, voltage across the inductor on the forward converter is equal to minus V out, isn't it? When the switch is off, what is voltage across the inductor? When the switch is off, this diode is on, right?
Negative
And
V
this,
out.
yeah, so it's going to be negative V out, isn't it? So that would be the
Yeah.
easiest way, the easier voltage to work with. So you
Wait,
can,
that's
you
when
can,
the switch is off. Yeah.
that's correct, yes. So I'm not going to put the negative value. It's just going to be the absolute value, which is V out, times dt. We have the delta L. Delta IL is 3 amps. We have the delta IL. That delta T right now is T off. That's T off. And for single switch forward, T off is equal to 1 minus D times T. Right? So I think we have everything there, right? So LC is equal to V out. What is V out? 24, isn't it? If I'm not mistaken. Delta I is 3. And then 1 minus duty cycle. Ooh, do we know duty cycle? We haven't found duty cycle yet, huh?
We should have a formula for it.
Yes. We have V in and V out, and we have the turns ratio, don't we? Yeah, so if I know V in, V out, right, I know the duty cycle, then I know the output voltage is equal to V in times duty cycle times N2 over N1, right? Okay, so from here, I know V out, I know V in, I know N2 over N1, and I can solve for duty cycle. I'm not going to solve this with numbers, okay? Oops, actually, let me rewrite this. V out over delta IL, 1 minus D over F, right? We know V out, we know delta IL, we know frequency, right? And duty cycle, we got it from here, right there. All right. So once you get those, then you get LC. Any question on this? Maximum voltage across the switch. Across the switch. Across the switch. Right here, when the switch is off. What is voltage across the switch when the switch is off? That's going to be
Is it
reflected
VN?
voltage. Yeah, V in times the reflected voltage from the top winding, right? Let me redraw because it's already kind of bad. If I redraw just the primary side, when the switch is closed, you have this circuit right here. Right? And this is on the primary side only. So when the switch is closed, I have the plus minus V in right there. Right? And then it's reflected into here. Right? And then you can see we have voltage across the switch over here. So that's going to be what? By KVL around this loop
VN.
is V in plus V in N1 over N3, right? So you have V in right here. I'm looking at this loop right here,
Okay, perfect.
right? V in plus V in times turns ratio, that voltage is this voltage. Right. Any question on this? No? All right. No questions?
Professor, can you please go back?
To this?
Yeah, okay. Okay, it makes sense.
Okay.
Thank you.
Any other questions
From this problem or from any other problem?
from this problem? No? Any other questions? If not, let's see if I can look at one more problem from the previous chapter.
Oh, okay. Because if not, I was going to ask about
Oh, go ahead.
843.
843.
843. Uh-huh. Because I don't feel extremely strong on the isolated isolated configurations.
Okay, we can do 843. 843. It's a flyback. CCM, the converter has the following parameters: N1 over N2, magnetizing 1.2, calculate input voltage. Okay, so I'll draw the flyback first. It always helps me by drawing it first. So let's see. And then we put in all that we know. Okay, what do we know? We know 1 to 2, 1 to 4. And then what else do we know? We know 1.2 millihenries of the magnetizing. Okay, 1.2 millihenries. And what else do we know? We know, we know this
The
current,
switch current.
the switch current. Okay, so the switch current. Okay, so the switch current. And the value of it is
So
0,
we
4,
know the duty cycle, right? From
0,
the
4.
graph.
Yes, we know the duty cycle. And micro 19 to 21. Okay. All right. So we know switching frequency, right? We know switching frequency is 1 over 10 micro. What is that? 100 kilo, maybe? And then, all right, 6 divided by 10. Yeah, it is 100 kilo, right? And then we know delta ILM, right? We know ILM min is equal to 19 amps.
19.
ILM max is equal to
21.
21 amps. And duty cycle, we know is equal to 4 out of 10. That's 0.4. Okay. What is it asking? Input voltage. Input voltage. Input voltage. Okay. So input voltage, we should be able to get it from the slope, right? When the switch is on, when the switch is on, we are charging this inductor, right? Right here with V in over LM slope. What is voltage across that inductor VLM? It's V in, isn't it?
VN. Yeah.
VL, which is equal to V in, is equal to LM delta IL delta T. Right?
Yes, sir.
So do we know LM?
We do.
Yes. Do we know delta IL? Yes.
Yes.
Do we know delta T?
Yes.
Yes.
That's the T on, right?
That's correct. So that's going to
Okay.
be T on, which is dt, right? And delta IL, which is 21 minus 19. And then we know LM, we know this, and we know this, right? That good? So we got the in from there. Yes? Any question on this? No? Or do you want to solve it? Or it's okay, just leave it like this? Part B, average output voltage. Once you know B in, once you know duty cycle, right? So this is B in already, right? So we know B in. Part B asks for
B out average, which we can get it.
right, B in times D over 1 minus D times N 2 over N1, right?
Yeah.
Do we know B in? Yes, from here, from part A. Do we know duty cycle? Yes, we do, right? Do we know
Yep.
N2 over N1? Yes, it's given,
Yeah.
right? Okay,
Yep.
so we should be able to get B out from there.
Mhm.
Part C, or part C, average input current. What is that equal to?
Average input current.
Well, average input current is this current right here.
Oh
Right.
yeah. Oh, we can just
So-
so what we did before. Find the average. Find the area.
That's correct. Yes.
Okay.
Yeah. So I in average
Professor?
should be equal to I switch average. Yes. Go ahead.
Nothing, I was calculating something wrong.
Okay. Any questions? So part C should be the area or the average value of the given waveform. Okay. Right. So I in is equal to I switch, right? I in average is equal to I switch average. Part D, primary winding current when the switch is on. That should be easy. What is the answer to this?
What is it? Primary wanting current switches on. Which is
Related to reset winding that we discussed earlier.
0.
Yeah, 0. Right. So when the
Okay.
switch is on, right? See what happens. What happens when the switch is on? When the switch is on,
And the switch is on.
Just charges the
And
magnetizing inductor.
yes. And then what? And then what happens with the diode here
When it-
on the secondary side? It's
the
open, right?
diode is
Yeah.
open. Yeah.
When the switch is off, the magnetizing inductance switches sides.
Yeah. So if diode is open, is there any current here on the secondary winding? No, right? 0 amps
No.
right here. Then
Yep,
go ahead
yep,
and
yep.
reflect it to the primary winding right here. So how much current do we have on the primary winding?
0.
0 amps. So where's the current
0.
coming from then? Only through here, right? Only to LM,
Yeah.
which is through the switch as well. So the again, it doesn't matter if LM is big or small, right? Current through the primary winding when the switch is closed is equal to 0, right? Oh, God, there's something wrong with the mouse here. Maybe the battery's out. All right.
Like us, we're out. We're out, Professor. We're done.
All right. Well, part E, peak current through the diode. How do you find it?
Current is it not the
Would
same
would you
as
have to
S3?
would
Is it
you
not the
have
same
to
as the switch?
Would you
related
have
to the
would
to
have
switch.
to
like flip
transform
that
it. You would have to
flip that
transform
current
it.
over with
One
the
second.
turns ratio
That's correct. Yes.
and the peak that would give you?
Right. So peak current through the diode, that's going to be the same as this peak value right here. This, remember, this is across, this is through the switch, right? This is on the primary side. Primary side. Diode is on the secondary side, right? So therefore, the peak value of the diode current should be the same as the peak value of the switch current times the turns ratio. I believe is was it N1 over N2? Am I right?
It's 1 and 4. I mean 4 and 1.
Yeah, for this for the V1 over V2 is equal to N1 over N2 is equal to I2 over I1, right? So I2, which is I diode, is equal to I1 times N1. Yeah, okay. This is the ratio I'm looking for. So it is N1 over N2. So that's the answer for part E. Is this peak value, which is 21 amps, times 4. Looks like it. N1 over N2 is 4. Okay. Any question on that one? All right. Any more questions? We have about 12 minutes left. We'll continue tomorrow, but let's see if I can. Oh, do you have any questions? Any more questions?
I have a quick question, if
Sure.
you don't mind.
Go ahead.
So mine revolves around buck converters. Do you
Sure.
remember why you would prefer using a MOSFET over a over any other type of switch?
Typically, it's MOSFETs because of the level of power that we use for buck converter. Buck converter is very good for low to medium power. Something around I would say 100 watts or less.
Mm-hmm.
And then for those type of power level, MOSFET is ideal. It's fast, right? But if you're looking for 1,000 watts application, you might want to look for a different device, such as IGBTs or any other device that can handle more power than MOSFETs.
Okay, so then MOSFETs are meant more for lower frequencies then? Lower frequency or no,
No,
high
high
frequency and low
frequency,
power.
low
High
power,
frequency,
yeah,
lower power. Okay, yeah.
right.
Okay.
So consumer electronics, right? Those are lower power, 60 watts, 50 watts, 30
Mhm.
watts. USB type of power supply, those kind of things. Those are good for MOSFETs. But
Okay.
yeah, if you have a 2 kilowatt power supply, 1 kilowatt power supply, you might want to look for a different device. IGBTs maybe. Yeah.
Okay.
Yeah.
So then if you were to choose in like a LDO and a buck, it would come down to how much voltage you're dealing with, right? Since LDOs are better for like a smaller differential between the input and the output voltage. So if you have like a 5 volt and you need to step down to 3.3, you'd rather want to use an LDO rather than a buck.
Also power, LDO is for lower power too.
Lower power consumption, yeah.
Yeah.
Okay.
So let's say if you're looking for 1 watt regulator, right? So the choice there could be buck, could be LDOs, right? Because they're small wattage, right? Only 1 watt. So yeah, those are the two options, either buck converter or LDO. But then which one is gonna be a better solution? That would be the one that you mentioned earlier, depending on the differential voltage between output and input, right? If the input is 15, the output is 5, I would still use buck converter. Because if you use LDO, that's already 30% efficient.
In our lab, I think we had like a high differential for one of the last samples, and it would cause the component to heat up a lot.
Yeah.
And it would like flicker between the voltage you were actually supposed to see between like some random value.
Right.
From our group asking you, something wrong with it? It happens because of the power dissipation.
Right. Yeah. Yeah.
Yeah.
Yeah.
Okay then. Well, I
All
think that
right.
was my question. I have an interview on
Okay.
Thursday, and they're like, "Hey, LDOs and bucks," and I was like, "Oh yeah."
But
I just
LDO
want
is
I
not a
just wanted
bug
to run
though.
it back again. No, yeah.
Yeah. Yeah. All right.
Okay.
Any other questions? Well, if not, tomorrow I still have another office hours, I believe, right? From what time to what time tomorrow?
1 to 4.
1 to 4. Yeah. So 3 hours. Now, what I'm planning to do, I want to go over this one problem, but I don't think I have the time today. It's only 8 more minutes. I'll show you. I'll share the screen. Um, a more complicated, problem from chapter 7 because we haven't done it yet, right? We've only done the simpler problems. Oops. Oh boy. Okay, let's see. Can you still see the screen?
We
Yeah.
can still see it. Yeah.
Okay. Something wrong with my mouse. Hang on. Has mine of its own. Let's see. Stop. Okay. So something like I would say something like uh, was it this one, right? Where you combine two topologies, such as this one. There's more, like this one. See this? Buck and boost, buck and buck boost.
What
Right.
problem is that one? 53?
Hmm?
53?
This one is, what is this one?
So I said that
54.
you point
54.
54. Okay, 54. And then the first one that you pointed out was 47, right?
Yes, 47, this
And
one.
54. Okay.
So at least I want to do one of those, if not more, something like this as well. But this one is homework problem, isn't it? Or no? It is, right?
That
I
one
don't,
was.
let me pull up my homework.
Can't remember.
It's
I
not?
have my homework. I have my homework here. Let me see. We
We've
have
done that one
42.
before. 40. We've done 40.
Yeah,
We
I
done
think this is homework, yeah.
40. We did 36.
42,
20,
44.
42, 44.
Okay.
We did 44.
Okay.
But 44 was a very difficult one from my perspective.
Okay.
That was rough.
If you want to like review it, I wouldn't get mad because
Okay.
that was a top one for me.
Well, I'll start with this one because these are different topologies, right? You have a buck and then you have a boost. So we're combining buck and boost. So maybe I'll start with this tomorrow, right? And then and then we continue with different types. So maybe this one. That's another combination, buck and buck boost.
What
And then
about 59, 60? What do you think about those 59 and 60, which is like one of the last
59,
ones?
59 and 60.
No, we gotta ask him to do the ones we don't have the solutions for that he provided.
Oh, so
Oh,
59.
only odd problems. Only odd
Only
problems.
odd. Only odd.
Yeah, yes. Yeah, so I can do 59 as well, let's see, it's 5 minutes.
57, 65. No, it's
Yeah,
Well, we
from
still
there and
have five
on.
minutes. Okay, let's see if I can solve it let's see if we can go over this in 5 minutes. For 59. Let's see. So source the current waveform through the output capacitor in ideal boost converter. Okay, that's boost converter. Operating in steady state CCM. The average output voltage in the converter is 15 volts. Find the duty cycle. Find the duty cycles. You should be able to find the duty cycle from here, right? This is a boost converter. So this current waveform is through the diode.
It should be 4 out of 10, right? Because that's when the diode is low.
But hang on. Shows the figure 721 shows the current wave through the output capacitor. Okay, through here. All right. So the duty cycle should be right here. Yes.
Yeah, should be
But that's
0.4.
discharging, right?
Yes.
So the charging path is missing from the diode current. So yes, you're right. So duty cycle should be 6 to 10. So that's 4 microseconds divided by 10, right? 10 micro. So that's 0.4. Any question on this one? Okay. So that's part A. Part A is 0.4. How about part B? Average output current.
It's whatever that offset is.
Yeah. So how do you find the offset? This is a good problem. How do you find the offset? Anybody?
Would we look for the voltage across the inductor for the offset?
No?
So we have, can we get the area under that and then multiply it by the time? And that should give us like a voltage or something? Or is that wrong?
Almost.
Is the
Almost.
area, is
So
the
close.
area, right?
It's there. Has to do with the area. Remember, this is current through the cap, right? Current through
Yeah,
this
yeah.
capacitor. What is the average current through the cap equal to?
It's IL. Oh, wait.
No,
No.
it's
The average, is it
Zero.
out, it's the output capacitor, it's
Zero.
zero.
Area is zero.
What does that mean? What does that mean? The average current through the cap is zero.
The
That
top
means the
area
area
is equal
here.
to the bottom area.
Yeah.
Exactly. Don't we know the top area,
We can find it.
Yeah, it's easy to find.
right? So let's call it A1, right? Let's call the bottom one A2. Can you find A1? The answer is yes, right? A1 is equal to the area of the trapezoid. That's going to be 1.2 plus 1.4 times the height, which is, or the base, which is 6 micro, divided by 2.
Mhm.
That's the area. Well,
Yeah.
area 1 must be equal to area 2, right?
0.8.
Guess what's missing from area 2 is the offset.
Yeah.
That's what you're looking for, right?
Mhm.
Right. So that's the, let's call it I out average, right? So area 2 is equal to I out average times 4 microsecond, right? 6 to 10, right?
Yeah.
And so the only unknown is I out average. So that should be the answer for part B.
Oh, nice.
Okay. How about, is there any question for part B? Okay, so equal area, right? That's the key, equal area. All right. Part C, input voltage. Ooh.
Is that not through the inductor? The current through the inductor?
I do have the average output voltage, 15 volts. And I know duty cycle.
Yeah.
You
so
can find V out,
Yes.
and then if it is ideal, we can just solve for that.
Yeah,
Okay. Yeah. There you go.
right.
Yep.
That's it. That's 5 minutes or less than 5 minutes.
Okay.
Dang.
Doing it with the professor. On the test, if you want to be with us, that's fine. You can be my
But-
partner. I don't get mad.
You make this look so easy, and I know on an exam I'll be like, I don't know.
Any question on this problem? We'll continue tomorrow with that. All right. It's 3 o'clock.
Thank